In January 2026, a team of scientists stood on one of the most dangerous glaciers on Earth. Beneath their boots was more than a kilometer of ice, and beneath that ice was an ocean they could not see. They had come to find out what was happening down there, so they began drilling. Not 10 meters, not 100, more than 1,000 meters through moving Antarctic ice. Their target was the hidden space where the glacier meets the sea, a place with no sunlight, no easy way in, and almost no direct measurements. When the drill finally broke through, the instruments reached water, but it was not still, it was turbulent, it was relatively warm, and it was melting the glacier from below. Then the glacier did something else. It moved fast enough to trap part of the equipment inside the ice. This was Thwaites Glacier, the so-called Doomsday Glacier, and the question is no longer whether it is changing. It is. The real question is much harder. Are we now watching the early stages of a process scientists have feared for decades? Thwaites sits in West Antarctica, facing the Amundsen Sea. It is enormous, roughly 120 kilometers across, so wide that the scale is difficult to understand from the ground. But size is not what made Thwaites famous, its nickname did. The Doomsday Glacier, it is a name that sounds like clickbait, and if we are not careful it can become exactly that. Because Thwaites is not about a giant block of ice suddenly disappearing tomorrow. The real story is slower, more complex, and in some ways more disturbing. If Thwaites were eventually lost completely, the ice it contains is equal to roughly 65 centimeters of global sea level rise. That does not mean 65 centimeters next year. It does not mean the glacier is about to vanish. But it does explain why scientists watch this place so closely. Thwaites is also tied to a much larger part of the West Antarctic ice sheet. So the concern is not only the ice we can see at Thwaites, it is what changes there could mean for the ice farther inland. For decades, researchers have watched the glacier thin, lose ice and retreat. The warning signs did not arrive in one dramatic moment. They built slowly year after year, measurement after measurement, until one question became impossible to avoid. What is making this glacier so vulnerable? To answer that, we have to stop looking at the top of the ice. We have to go underneath it. There is a boundary beneath Thwaites that most people will never see. But it may decide much of a glacier's future. It is called the grounding line. On one side of that line, the ice still rests on the seabed. On the other side, the ice begins to float. That sounds simple, but the position of this line matters enormously. Much of Thwaites sits on ground that is already below sea level, and farther inland, parts of that bed become even deeper. That creates a dangerous shape. Picture a bowl that becomes deeper as you move inland. If the edge of a glacier retreats into a deeper ground, the ocean can gain access to more ice instead of less. That is why the shape of the land beneath Thwaites matters almost as much as the weather above it. If the grounding line moves backward into deeper water, more ice can be exposed to the ocean. That can allow the glacier to lose support and retreat farther inland. This is one of the reasons scientists worry about Thwaites. Not because it is melting like an ice cube in the sun, but because the glacier is connected to the ocean from below, and the land beneath it does not give scientists much comfort. The deeper the grounding line retreats, the harder the system may become to stabilize. That does not mean runaway collapse is certain. It means the geometry gives the glacier very little room for error, and there is another problem. The ocean beneath Thwaites is not simply cold, quiet water. Some of it is warm enough to melt the ice from below. When people picture Antarctica losing ice, they usually imagine warmer air and melting on the surface. At Thwaites, one of the biggest threats comes from the opposite direction, from underneath. Relatively warm ocean water can move beneath the floating part of a glacier and toward the grounding zone. Warm here does not mean warm enough to swim in. It means warm compared with the freezing point of seawater, and that small difference is enough to matter. Previous research has already shown that melting beneath Thwaites is not even. Some flatter areas melt more slowly, but sloping ice, terraces and deep cracks can melt much faster. That means the water does not simply wear away the bottom in one smooth layer. It can attack weak shapes, it can widen cracks, it can change the underside of a glacier in ways that are difficult to see from space. And that creates a serious problem for scientists. The most important part of the story is therefore hidden from normal view. A crack seen from the surface tells only part of the story. A change in the water beneath the ice may begin affecting the glacier long before that change becomes obvious from above. Satellites can tell us a great deal about what the surface is doing. They can measure movement height, ice loss, retreat, but a satellite cannot simply look through a kilometer of ice and watch the ocean moving underneath. For that, scientists had to go there. They had to drill through Thwaites itself. In January 2026, a UK-Korean research team reached a remote part of Thwaites Glacier's main trunk. This was not a normal field site. The ice was fast moving, the surface was heavily crevassed, the area was difficult to reach and difficult to work in. Yet this was exactly where they needed to be. Their plan was to use hot water to melt a narrow borehole through the glacier. The target depth was about 1 kilometer. Imagine the scale of that, a hole only wide enough for scientific instruments, dropping straight down through more than 1,000 meters of Antarctic ice. The team was working close to one of the most important parts of the glacier. Near the grounding line, the zone where ice stops resting on the seabed and begins to float. This is where the ocean can reach the glacier from below, and it is where small changes can have large effects. The mission had one simple purpose: stop guessing, measure the water directly, measure the conditions beneath the glacier, and find out what the hidden ocean was doing to the ice above it. By May, the team had an answer. And this is where the story moves from prediction to direct evidence. For years, researchers had used satellites, ocean measurements, radar, and computer models to build a picture of what might be happening in these hard-to-reach areas. Now they were about to put instruments into the water itself. The drill went through more than 1,000 meters of ice, then it broke through. For the first time, researchers collected ocean data from beneath that part of the glacier's main trunk, and the water was moving. British Antarctic Survey reported turbulent, relatively warm water beneath the ice. Water that was actively melting Thwaites from below. That is a key point. The ocean beneath the glacier is not just sitting there, it is part of the system changing the ice. Scientists had suspected this kind of interaction for years. Other missions had already shown warm water and complex melting near parts of the grounding zone. But this mission gave them direct measurements from a part of the glacier that had been extremely hard to reach. And then the fieldwork produced one detail that shows just how difficult this place is. The researchers wanted to leave instruments beneath the glacier so they could keep collecting data over time, but Thwaites kept moving. The ice shifted fast enough to trap the equipment. The long-term setup could not be completed as planned. Think about that. They drilled through a kilometer of ice to reach the hidden ocean. They got the data, and then the glacier itself closed around the equipment. That is not proof that the glacier is about to collapse, and this distinction matters. A dramatic field result is not the same thing as a countdown clock. The discovery tells us about the forces acting on Thwaites now. It does not tell us the exact year, decade, or century in which every possible consequence will occur, but it is a powerful reminder of what Thwaites really is. Not a frozen object, a moving system, one that is being changed by water beneath it while the ice above continues to float toward the sea. And even that is only half the story, because the ocean is not the only thing hiding beneath Thwaites. Under the glacier is a landscape, rock, sediment, water, and in places hidden lakes. A 2026 seismic study gave scientists a much clearer picture of that hidden ground. The results showed that the bed beneath Thwaites is not one simple surface. There are hard rock ridges, there are areas filled with softer sediment. There are water systems beneath the ice. And researchers found evidence of an active subglacial lake linked to thick, water-filled sediment. Why does that matter? Because what the glacier slides over can change how it moves. Hard rock can create resistance. Soft, wet sediment can allow the ice to move more easily. Water can reduce friction beneath parts of the glacier. So, when we ask why Thwaites moves the way it does, there is no single answer. The ocean matters, the shape of the bed matters. The sediment matters, the water under the ice matters, the grounding line matters. All of these pieces interact, and this is exactly why predicting Thwaites is so difficult. It is not one problem with one switch, it is a large system with many connected parts. Change one part and another may respond. That uncertainty is not an excuse for panic, but it is also not a reason to ignore what scientists are finding, because the past has already shown that Thwaites can move much faster than we once thought. Satellites have watched Thwaites for only a small part of its history, so scientists looked elsewhere for clues. They looked at the seafloor. The ground in front of a glacier still carries marks left by the ice when the grounding line sat farther out. Those marks are like a record, a frozen history written into the seabed. In 2022, researchers published evidence of a past period when the grounding line retreated at more than 2 kilometers per year across part of the area they studied. That number needs context. It does not mean Thwaites is retreating at that rate everywhere today. It does not mean the same thing will happen tomorrow, but it proves something important. Under the right conditions, very fast retreat has happened here before. That changes the question. We are no longer asking whether Thwaites is physically capable of retreating quickly. We know it is. The next question is whether the conditions that allowed rapid retreat in the past could appear again. That is why the old marks on the seafloor matter so much. They are not a prediction, they are evidence of capability. They show that Thwaites has another gear, and the modern record gives us another warning. Evidence from sediment cores suggests that significant retreat at Thwaites began around the 1940s. So this is not a crisis that suddenly appeared because someone gave the glacier a frightening nickname. The retreat has a history, decades long. The 2026 drilling mission did not discover the beginning of the problem. It gave us a new view of a process that has already been unfolding for a long time, which brings us back to the question in the title, has Doomsday started? If by Doomsday we mean that Thwaites will disappear next week, the answer is no. If we mean that the world's coastlines are about to change overnight, the answer is no. And if someone tells you scientists know the exact date when Thwaites will collapse, they are telling you more than the science can support. Current research does not say that total collapse is about to happen in the next few years. In fact, the wider scientific assessment says full disintegration is unlikely in the next few decades. That matters because fear is easy, accuracy is harder. But accuracy does not make the story less serious. It makes the real warning clearer. Thwaites has already been retreating for decades. Warm ocean water is already reaching beneath the glacier. Scientists have directly measured relatively warm, turbulent water melting the ice from below. The ground beneath Thwaites contains rock, soft sediment and active water systems. The glacier has retreated very quickly in the past, and its future matters because of a much larger body of West Antarctic ice behind it. A complete loss of Thwaites alone would not happen in one sudden event, but over the long term, its ice is equal to roughly 65 centimeters of global mean sea level rise. For coastal communities, ports and low-lying cities, even smaller increases matter because sea level rise raises the starting point for storm surges, high tides and coastal flooding. That is why centimeters on a scientific graph can become very real at the shoreline. So has Doomsday started. Maybe the word itself is the problem. Maybe we keep waiting for one dramatic day, one crack, one collapse, one moment when the world suddenly knows something has changed, but large systems do not always fail like that. Sometimes the important part happens first, quietly. A line moves backward, a cavity grows, warm water reaches farther under the ice, a crack becomes deeper, the glacier loses a little more support. And then the same thing happens again and again, for years, for decades, until the map looks different. Maybe the frightening thing about Thwaites is not that Doomsday arrives all at once. Maybe it is that a process can begin long before most of us realize it has begun. At the bottom of the world, scientists drilled through more than a kilometer of ice because they wanted to see that process more clearly. They reached the ocean beneath Thwaites. They measured water moving in darkness. They found it warm enough to melt a glacier from below, and while they were trying to watch it, the moving ice trapped their equipment. None of that tells us the exact future. Science rarely gives us that luxury, but it tells us something we should not ignore. The forces that make Thwaites dangerous are not theoretical, they are already there. The glacier is already changing, the ocean beneath it is already doing work. And the question now is not whether Thwaites has a problem, the question is how far that process will go, and how much time the world has before the changes at the bottom of a planet are felt far beyond Antarctica. The name Doomsday Glacier makes us imagine an ending, But Thwaites may be teaching us something very different. Doomsday may not be a day, it may be a process, one that begins quietly under a kilometer of ice in complete darkness where almost nobody can see it happening, and that may be the most unsettling part of all. If you found this investigation valuable, subscribe to The Final Statement. We build these stories from original research, documented sources, and our own narration. And tell me in the comments, do you think the name Doomsday Glacier helps people understand the danger, or does it make the science harder to trust? Until next time, this is The Final Statement.